So good morning, or maybe be better, good evening or good night, Professor Subhas there at Sydney. So Professor Subhas is a distinguished lecturer at IEEE Sensors Council. He's currently working as a professor of mechanical electronics engineering at Macquarie University in Australia, and is the discipline leader of the mechatronics engineering degree program. He's a fellow of IEEE, a fellow of IET, a fellow of IET in India, and a topical editor also of IEEE Sensors Journal, and associate editor of IEEE Transactions on Instrumentation and Measurement, and IEEE reviewer of biomedical engineering. He's also editor-in-chief of an international journal of smart sensing and intelligent systems, and he has been a distinguished lecturer of IEEE Sensors Council from 2017 to 2022, and is the founding chair of IEEE Sensors Council New South Wales chapter. So please, Professor Subhas.
Can you see my screen, Carlos?
Yep.
Okay, so thank you very much for your nice introduction. And actually, congratulations for the autumn school you are organizing today and tomorrow. So I will actually start with few words about IEEE Sensor Council before I go to my topic. So Australia, we traditionally welcome to the country. So I like to acknowledge and pay respect to the Darug people of the Eora Nation, the traditional custodian of the land. We pay our respect to elders past, present, and emerging. So Carlos has talked about IEEE, so I will not go through that. So IEEE Sensor Council, he has also mentioned. IEEE Sensor Journal, which is improving in terms of more on the impact factor as well as download. So I'll tell few words about the chapter which we formed in New South Wales. So the chapter we formed was approved in 2019, September 25th. Officially, we started the chapter from 4th of December 2019. These are our current members. So I'm continuing as the chair. I'm actually looking for someone who will be taking up the post of the chair. In 2020, we have 25 activities. And based on that, in 2021, we got the Best Chapter Award in 2021. In 2021, we have 23 chapter activities. One of the things we started is Best PhD Thesis and Best MRes Thesis Award. I think I heard from Carlos that the Spain chapter also doing that. So that's a very good thing to acknowledge and recognize the best work happening in the area of sensor. We also organized the IEEE Sensor Conference 2021. I was the general co-chair, but unfortunately, it did not happen face-to-face. It happened online. Because of online, the number of submission was relatively less. So we had only 568 submissions and 333 papers were accepted. In 2022, so far, we have 19 total activities. Out of that, 15 activities or technical activities, and we organized the spring school in September. Also, we are continuing that best PhD thesis, and our AGM will happen on 7th of December. So our spring school was on September 19 and 20. We had second day was hands-on activities. That was quite exciting for the master's PhD students. And this will be something which we like to continue. We also recently had Women in Sensor workshop, which happened last week. And we had 5 speakers who spoke about different area of sensor. So of course, Sensor Council, we always get support, and IEEE here, New South Wales sections, and other universities, they also provide their support. And this is the information-based PhD thesis. Okay, so with that, I will go to the actual topic of today. So today I'll be talking on wearable sensors for health monitoring. Our university, Macquarie University, has contributed on the development of Wi-Fi in late 90s. So Professor David Scallan and Professor Neil West, they were the professors who worked on IC for the Wi-Fi. And of course, we all know that Wi-Fi is very important for our life now because we use internet, and connectivity through internet is one of the medium is Wi-Fi. Our university was established in 1964, and we have around 40,000 students, and we are 195 in the world ranking by QS. My research is, of course, in the area of sensors. We develop sensors. We also make sensing system. Sensors are very important for any system as well as for anyone who like to measure something. Lord Kelvin told that if you cannot measure it, you cannot improve it. So for measurement, we need sensor. Also, there are many sensors which are used as medical devices for monitoring physiological parameters or health-related parameters. That can be as simple as thermometer for measuring body temperature, or maybe very complex such as MRI scan, CT scan, and so on. Wearable devices, they are owned by the human body. Any part of the human body. These wearable devices has got powerful sensors, but they are very lightweight, tiny, and they measure physiological parameters based on which we know about the physical conditions of the human. These wearable devices are also known as wearable gadgets, wearable technology. Sometimes we call only wearables. As we can see, the development of the high performance semiconductor circuits, display devices, different smart materials, all these things made possible for the development of smart wearable devices. These wearable devices, they can include different sensors, simple as it is accelerometer, or complex can be EEG, and they can be used from any part of the body. On the head can be as headband, can be as a badge, can be as a camera clips, or as a smartwatch, or also can be part of clothes. There are different applications of wearable devices. They can be used monitoring physical or psychological stress, hydration status, or metabolism, for providing biological, physical biofeedback, muscle stimulations, haptic feedback, cognitive feedback, also can be used for training, monitoring and promoting sleep, evaluation of concussion. So there are many, many applications of these wearable devices for our day-to-day life. The recent trends of wearable and medical devices is going towards called Internet of Medical Things. These wearable devices and medical devices, they actually generate and collect, analyze and transmit data coming from our health-related parameters. Those data, if we can actually store and use it, that will provide a huge infrastructure, which will be a connected infrastructure of health system and services. So that Internet of Medical Things can provide a lot of advantages. As we can see, that will decrease the cost of healthcare, that will improve the diagnosis and treatment, that will also improve the disease management, that will improve monitoring chronic diseases at remote locations, that will enhance the patient's experience, and also it will improve drug management. So there are lots of benefits of this IoMT. Interestingly, what we can see is the growth in this sector. 2019, we had market around $18.75 billion, which is going to be $142 billion in 2026. So this is very important that it is growing very fast. And it's not growing in one particular region of the world, it is growing almost all parts of the world. Next 5 years, there is a 4 to 5 times growth in almost all parts of the world. Amount may be different depending on the region, but the growth rate is almost similar. If we see the growth, actually, interestingly, this is almost 1/3 on medical devices, 1/3 on wearable devices, and 1/3 on implanted medical device. So I'll be talking most of the 3 things in my talk today. Now, the companies which are playing significant role in this Internet of Medical Things, whether it's a wearable device or medical device or implanted device, they're all listed here. General Electric, Biotronic, Boston, Medtronic, Johnson & Johnson, Cisco, Welch Allyn, IBM, Siemens Healthcare, Philips, and so on. So if we see the periphery of this IoMT consisting of wearable device and medical devices, they can be coming from anywhere, whether it's coming from a doctor or coming from nurse or coming from hospitals, clinic, or even for different types of apps which you use in smartphone. It can come from anywhere, and that's why the periphery is quite wide. So when we collect the data from those different systems, where do we actually store them? That's very important. This is some example that we have got different apps in our smartphone. This can be used for collecting data. This is not actually health data. This is like exercise, how many steps I have done on a day or a week or a month or years. That can show, and that can be stored. It can be actually uploaded into that system where data is stored. So in terms of the architecture of this IoMT, as we are collecting data from different sources, it is important to store them. Where do we store them, which will be accessible to all the sources of data where we actually collect? So important thing is that it will be in the cloud. And what we need to make is that all the devices which are collecting the data, they need to be connected to the cloud. Of course, this connection should have the security aspect fulfilled, and we will be able to store them, analyze them, providing access to the persons who are entitled to, but this will be the way to go. So in case of wearables and IoMT, the connections, the building blocks, we have the sensors, which is the measuring the physiological parameters or health parameters. We need the embedded processing, and those are all connected to the cloud with the help of internet connectivity. This can be Wi-Fi or LoRa or any other internet system, wireless communication systems we can have. And then we need to make sure that system is fully secured. The data will not be accessed by anyone who does not have the rights to access. The security will play an important role in this system. What we see in last decade, there is significant improvement in cellular, Wi-Fi, display and video system, but one of the bottleneck what we can see is the battery. The battery has not improved that much what we would like it to see. In the last 10 years, the battery has improved only 2.2 times, which means that same size battery now give only 2.2 times energy. There is a need of improvement of battery, either battery capacity as well as battery reliability. Yesterday in the news, I have heard on television that last 1 year, the number of accidents has increased 10 times in Sydney. So battery need to be more reliable. Our work in terms of the wearable system started in the year 2004, 2005. We are working on that for quite some time. Started this work. Our main target was how can we detect the fall by elderly people. In many situations, the elderly people, they fall and they have a lot of accident, people died. So we started with finger strip where we can actually have accelerometer and some kind of heart rate detection sensor. Then we extended it to wristwatch. Again, here we have the body temperature, accelerometer, and heart rate. Accelerometer is used for monitoring whether the person has fallen down or so. We extended it to emotion recognition systems using the same sensors, blood body temperature, heart rate, and here body conductance. And we can find, with the help of simple classification technique, we can find the emotions such as sad, happy, and angry with an accuracy of around 86.5%. Big picture of our research is called smart home, which provides a safe, sound, secure, and independent living environment. And this is very important because the life expectancy is increasing, and we can see in last 50 years, people live much more longer than before. But at old age, people need help. This is, of course, at the age of 75, 80, and so. But even at young age, there can be incidents which can lead to death. This particular person was living alone. He has died due to some unforeseen incident, and his body was discovered after 20 days. This type of incidents are not very rare. They are very common, happening in many parts of the world. And the reason is, as we can see, big cities like Stockholm or London, over 50% people living alone. This is one-person household. And this is happening in many parts, many big cities in different countries, whether it's US, Finland, Ireland, Japan, US, UK, and so on. So this is very important, that how do we develop the technology which can take care of this situation. So our idea is, with the help of sensor and instrumentation, if we make wireless sensor network or Internet of Things based network, those sensors can monitor different activities of the persons. It can be either wearable or even non-wearable. Data is measured on real time and stored and analyzed. We can actually tell whether something is not regular. That's the idea of this type of work. So over the years, we have developed different sensing system. Either sometimes the sensor can be readily available in the market, we make the sensing system, or also we develop sensor for certain applications. And we install the sensors in a very old home, converting the old home to a smart home. And that's what we call is a living lab. Different types of sensors are installed at the home. They can measure electrical appliances, different types of sports-related sensors, which measure chair, bed, sofa, and so on. We also can monitor the movement of the people using PIR sensor. And then, of course, we have room temperature, where monitor temperature and humidity. If you have the options of wearable sensors, that will be really good. We can also monitor physiological parameters. Communication technology can play an important role. What type of wireless communications we will be using? We would like to have a standard protocol. So whether IEEE 802 or LoRa, that depends on the applications. We have developed with the Zigbee, and recently we make it Wi-Fi. So this is called technology assisted home. Sensors and technology, they can make any old home to a smart home. On real time, we monitor the appliances with a timestamp. We collect the data, and the raw data is collected and stored and then analyzed. After the analysis, we determine what activity the person does. And then from there, we can tell what's the wellness of the person, how well the person is. This type of system consists of sensors, which is the hardware, sensors and instrumentation, communications. But then when the data is communicated and received, then all is data analysis or data analytics. So software play an important role. We need to develop different intelligent algorithms, different intelligent programming, and that can be for determination of the activity and behavior. It will be activity annotations, some kind of probabilistic approach, time series analysis, and also some kind of pattern matching. All these things will lead to the detection of the behavior or detection of the wellness. It is important sometimes to know what type of sensor need to be used. It is a very complex decision. It also depends on the person's and his or her day-to-day life. But what we can do, we can start with some simple system and we can install them, and we can then see whether something is not used at all. So the frequency of sensor usage, how frequently someone using a sensor, that will decide whether the sensor needs to be used or not. We find some wellness function. These wellness functions can tell how well the person is. We have two types of wellness function. One is based on inactive usage. That means the person is not using any particular sensor. Based on that, we defined a mathematical equations, beta 1 equal to 1 minus t small t by capital T, where small t is the total duration of inactive duration when there is no sensor is used. Because sensor is only giving the information. If the sensor is not used, we will not be knowing anything about what the person is doing, provided the person is not having any wearable sensor. And capital T is the maximum inactive duration, which will tell us the person is still well. It starts with 100%, and then it's slowly decreasing with time, and we can decide when is the threshold. Threshold can be either 50% or 60%, and then when it goes below threshold, we can generate a warning message. That's what we'll do. We also define another wellness function, which is beta 2. This is based on excess usage. Excess usage is very important for certain appliances. For example, if somebody sleeping on bed, normally maybe sleeping on 8 or 9 hours, but if due to something the person using more time on bed, that means there can be some issue. Person might not feeling well. So this can lead to early detection of the person's problem. Again, here also, it starts with a very high value, more than 1, and slowly decreases with time. And then it actually goes below certain value. This data, what we are collecting, can be analyzed, past data, and they can be analyzed and they can be telling us what's the trend of the person's daily life. So prediction of the future behavior. So we can actually predict the future behavior of the person based on the data we collect. So this is very important for any home monitoring system. This prediction, which is also called trend, we can actually predict and then we can verify it, because we will be going, the present will be going to the future. So we can actually verify, and we can see that some verification, they're very close to each other. So this type of data for monitoring a person is very, very useful. We can detect any problem at very early stage. And if I can detect the problem at early stage, it can actually help us to start the health management. We also do some research on EEG-based system, which is also a type of wearable device. This EEG-based system, they collect the brain waves. So there are different types of brain waves coming out of our brain: delta, theta, alpha, beta, gamma. Depending on the frequency, delta is up to 1 to 3 hertz, theta is 4 to 7 hertz, alpha 8 to 13 hertz, beta 14 to 30 hertz, and gamma 31 to 30 hertz. Now, as you can see, each one has got due to certain state of mind. For example, if we see theta, it involves mental workload or working memory. Now, there are different applications of this Muse-based system, which we have used here for our detecting our brainwaves. One of the research we have done, what is the effect of music on the brainwaves? And we have taken experiment of around 30 male and 30 female. What we have seen that females are more responsive than males to music. Of course, that may not be true, but the music what we have used, only 5 types of music: classical, jazz, neutral, pop, and rock music. Those genre music are actually, females are more responsible than male. We also working on the EEG-based mechatronic system. So this is BCI, brain-computer interface type of EEG system. And this we are using to detect the brain waves to know whether we can actually use these brain waves to control a mechatronic system. So this is something also we are currently working on the wearable domain. I will tell a little bit about our fabrication work, which we are doing. So effectively, we also fabricate sensors in our lab, and this sensor is capacitive type of sensor, planar interdigital sensor, which can be either MEMS-based or can be flexible material-based. MEMS-based sensor based on MEMS technology, silicon technology, that is of course rigid and can have many, many applications. In 1-inch wafer, we can have 21 good sensor. And then in recent times, we develop flexible material-based sensors. One of the good thing about the flexible material-based sensor is that any university, they do not have high-end infrastructure. With simple infrastructure, it is possible to fabricate MEMS, flexible material-based sensor. One of the important applications of the flexible sensor is in wearable domain. This can come on the clothes. It's a very good candidate for detection of any kind of stress and strain. As the physical dimension, they get stressed, physical dimension changes, and it is possible to determine what is the capacitance value we have. In terms of the fabrications, we have explored different types of material. In terms of the base material, we use PDMS, PET, or polyimide film. Depending on the material, we can get some of the advantage and some disadvantage. So the material selection is very important. In terms of the electrode, we use either carbon nanotube or graphene or aluminum. So it depends on what is the applications and what can be the material and what can be the electrode material. In the last few years, we have fabricated different types of sensors here at Macquarie University, and they are used either for healthcare related applications, or can be industrial applications, or can be environmental monitoring. So one of the applications of this is early detection of osteoporosis. Osteoporosis is a problem related to bone. The bone becomes brittle, bone breaks. Almost 1 in 3 for women and 1 in 4 in men above 50 are suffering from osteoporosis. So this osteoporosis problem, if we could detect at early stage, then health management can be done. And there is a high possibility that person can be recovered. When the bone breaks down, produce among a lot of things called C-telopeptide, type 1 collagen. The amount of C-telopeptide, type 1 collagen increase in the blood. So our sensors, we can make sensitive to that with the help of a specially designed polymer, which is functionalized on the top of the sensor surface. With a few drops of blood, this can be possible to detect the C-telopeptide. And we have compared the result with the standard laboratory system, ELISA-based system, and we can see that the error is under 3%. So this is quite exciting. And also the data which we measured can be uploaded to cloud. When the result goes beyond the value, which is problematic with respect to the health data, general practitioner or GP can take corrective actions. She can call the persons, and then extensive analysis can be done. So this type of sensors can be used as a point of care devices at home, and they can be IoT-enabled sensors collecting the data and putting the data in the cloud. So that's what this is very, very useful. What we aimed as, instead of using the blood, whether we can use urine. In order to use urine, we also need to have some other parameters to measure, and they are creatinine and calcium. Instead of one sensor, we now need a sensor array of at least 3 sensors, and that can be installed on the toilet, so the toilet becomes smart toilet for future. You do not need to collect the samples. It will be automatically measuring the parameters and uploading the data in the cloud. Of course, the environment is very robust. So because it's the sample is not simple sample, so that can be one challenge for developing high long sensor. My last topic today is the implanted sensors based on flexible material. This is basically used for addressing the lower back pain with the method called lumbar interbody fusion, LIF method. When people are suffering from back pain, and the worst case, there can be a surgical treatment, which is known as lumbar interbody fusion. And this basically addresses the lower back pain. In this surgical treatment, the aim is to immobilize the painful area of the spinal segment. Usually that is unstable and degenerate. And the doctor, what they do, they make that portion immobilize. And this interbody cage goes into the intervertebral space and secured by screws that prevent or restrict or reduce normal movement, as we can see here. I will show you one video. Hopefully this will work. Bear with me, please. So as you can see that when this operation happened, doctor basically used this interbody cage, and in order to hold that, they use different screws, as there are different other images here we are showing. The idea is what actually the doctor wants. Now, there is once the operation happened, there is no way the doctor would like to know the status, how this operation is happening and how the person is adjusting with his new interbody cage. This operation has now becoming more and more popular. In 2015, almost 200,000 people had this fusion. And this fusion is that this interbody operation is actually quite expensive. In Australian money, it's almost like $60,000 per operation. So that's what, if you see the total cost, almost $10 billion. So when the doctor does the operation, they feel that they are satisfied with the operations, but they face a lot of issues. The most important issue is that the biomechanics that promoting these fusions are still not well understood. There are problems which is related to operations. For example, the migrations of this interbody cage into the vertebra, screw get loose, screw sometimes break. So these are the different mechanical problems happen. When this type of problem happened, of course, the patient, they face the pain, they come to the doctor, but there is no way doctor can actually detect that. There are some imaging techniques available, but most of the imaging techniques are not very suitable for this type of applications. Most important thing that when the operation's done, doctor would like to know how is the sharing of the pressure and the load is happening between the interbody cage and the spine. So that's why the doctors are very much interested, surgeons are very much interested to have some kind of sensor. So whole idea of these implanted sensors for continuous monitoring is that how this fusion is happening after the operations, how it is slowly becoming solid, how the sharing of the pressure and the force, as well as where is the pressure are more, how the pressure is distributed. So there are many things doctor would like to know. And that's why they would like to have sensors for these applications. Specifically, the aim of this type of research is that when the implant is starting to migrate into the vertebra, how the bone growth is progressing with time, whether the implant is aligning properly with the bone, whether the joint is stable or unstable, whether any kind of fixation is needed at early stage, and also patient-specific rehabilitation program, whether they are required. So these are the challenging questions what the surgeon would like to know. So this is the interbody cage. We would like the sensors in between to determine the pressure and the stress happening. And of course, we want to get that information outside. So at this stage, we have made the sensors and we have done experiment with the wired and powering the system. But whole idea is that we will be not connecting the power from the power supply. Basically, we will be providing the RF power, which will be harvested by the sensors. And of course, sensor provide the information. And then that information will be communicated and which will be measured by the external circuit to know how it is the conditions inside. That's the whole idea of this research. We have done some finite element analysis to know how is the situation happening from the operations to the fusion to the bone growth, how is the load is shared, and so on. In order to do that, of course, we have used a complex system. We have used the computed tomography data. We have modeled the graft stiffness, fibers and ligament, joint articulations. Also, of course, for any finite element analysis, we have to provide the boundary conditions and assigning material properties. So these are the some analyses coming out of the finite element, stress strain analysis, both for flexion and extension. And we can see at the different areas such as soft callus, temporal stages, partial fusion, full fusion, and solid graft. How is the amount of pressure at different part of the interbody cage? And we can measure them, and we can show here that when the soft callus and slowly fusion is happening, initially it is high and then of course slowly reducing. But when it is fused, the interbody cage will be able to withstand more pressure than initial operations, initial period of the operations. So this is quite useful to know. And then of course we have fabricated sensors. At this stage, we have done experiment with the piezoresistive sensors, which has been procured from Amphenol with a size 2.5 millimeter by 2.5 millimeter by 2 millimeter. And this sensor has a pressure limit up to 2.5 megapascal. And it can actually capture the data as low as 1 hertz. We also fabricated sensors. I'll come to that. This is our experimental setup for the piezoresistive sensors. We have 7 sensors installed, 2 anterior left, 2 lateral left, lateral right, and center, and to the front area. We have applied around 900 Newton load distributed throughout, and these are the different parts where we have collected the result. And we can show here. And these are the different conditions, early fusion and solid fusion. We have simulated the environment of the early fusion and solid fusion. We can see that in the early fusion, pressure is more, of course, than solid fusion. It can withstand better force. And then we have compared the result of the experimental result with the finite element result. It is very heartening to see that the experimental measurement is in between the minimum and the maximum. And that is quite good that both the experiment and the simulation, they are very close to each other, which is very, very promising. And then we have fabricated the sensors based on capacitive sensors, interdigital capacitive sensor with the flexible material. One of the very good observations for us is to see that this type of applications, capacitive sensors are much more useful than resistive sensor. Here is the resistive sensor, which is providing the response, force and no force. And we see that very difficult to see the difference. But in capacitive sensor is quite significant that they are very distinct. Based on the fabrications of our capacitive sensor, we have lodged a patent in Australia last year, and we're waiting for the result of that patent. Of course, our plan is still a lot of work to be done. We want to improve the isolations. We want to reduce the size as well as thickness. We want to develop a RF telemetry for powering the system as well as getting the signal coming out of the sensor. So for powering, we are thinking of some kind of inductive power coupling. And also we want to reduce the overall size of the sensors. And then of course, we want to develop some kind of GUI for the software to see any kind of display of the data coming out of the sensor. So this is some things which are currently working on. And the progress is very slow in this area. It is very difficult to do something very quickly. In terms of the field trial, we are expecting sometime middle of next year, we will be able to do something with this sensor. So with that, I will summarize the talk. So basically, we work on sensors. Mostly it will be some wearable, including the implanted sensors. Our big picture, of course, that we can provide that sensors to human, monitoring some health parameters. And it can be used for a smart home applications where it can provide a safe, sound, and secure environment. Of course, in terms of research, we have to do a lot of work to improve the resolution, sensitivity, and smart electronics. With that, I will conclude here, and I'll be happy to take any questions and comments from you, audience. Thank you.
Oh, thank you very much, Professor Subhas. Thank you for the interesting talk. And now we have some time for questions. So, you have any question? So don't be shy.
Hello, congratulations for the presentation. It was very interesting. We are very happy to hear you. There is a small question. In my
Yes.
research field, I involved in a sensor of brain monitoring from the point of view of control theory. Recent publications in control theory, since 4 years ago, are saying that now our effort has not to focus in measuring more things. It has to be in being able to interpret complex data, being able to develop algorithms that are able to be embedded in microprocessors or FPGAs or computers that are able to do eigenvalues fast, Fourier transform fast, and all these new methods in machine learning and not supervised. So we are able to interpret all the data that we are getting from the sensors. So do you think that that's true, that we have to focus a little bit more on interpreting a complex data, or there is still a lot of develop in the sensors by itself?
It's a actually thank you for that question. It's a very I mean it's really close to the real research. So you have got two things. One is the data coming from the sensor, another is the data analysis. Now we have done lots of machine learning, especially on CNN and other method, to see whether we are able to get the informations what the especially our brain waves EEG sensor is giving in terms of the actual things what is happening. And we see that there is a error. Of course, we are getting accuracy around 83-84%. So what I feel that if we could make the sensors much more accurate, then the stress on the data or machine learning algorithm can be reduced, or in other words, with the same effort, we can improve the accuracy. So I think even though there are a lot of improvement happen in the sensor area, but still they are not 100% accurate. So there is an area of improvement can be possible to make it better. And then of course the algorithm can take its own course. So I personally feel that there is still some room for improvement on the sensor design and definitely on the algorithm development.
Professor Sabas, another question. We have a few minutes. Yeah, I have a question. So you just comment a few applications in the biomedical field. Could you please comment about the main barriers for these applications? Are they in technology, in the sensor design, or the regulations, or maybe the clinicians do not know very well the technology? What do you think are the main barriers for the application of these wearable sensors in biomedical?
I mean, there are actually different types of applications. Each has got its own issues. One of the main problem will be if you want to make anything clinical grade, then there will be no clearance from the concerned authority. That will be a big barrier, which will take quite some time because usually it goes through many phases and it can go up to 10 years. And as you can get a PhD students up to 3 years. So once PhD student finish, another PhD student come, you start from scratch. So for academics, it's quite a challenging part. In terms of the other grade type, so for example, if you have like a wearable grade for normal exercise type of applications, then it is not a big issue. You do not need to go through that rigorous standardization process. Even your country can do that. You don't need to go to FDI for that. So that can be quite simple. You need to make maybe quite a few, maybe 20 to 50 samples and do some clinical trial with the medical doctors, and you can get some permission. So it actually depends on what is the long-term goal, and that will decide what is the process you need to follow. But as for us, we are not working as an academic. We are working as an academic. We are not working as a research organization where we need to work on this product for 10 years. It's very hard for us as academic because we will be relying on PhD students unless you have got a research center. This is very, very difficult for us to go for the long-term goal.
Thank you. We have 1-2 minutes. One more question. So I have one more. Yes.
Yes, please.
Here and you. So what do you think is the most promising field after the previous question to work in the biomedical applications in the future?
So what I actually see in recent times, because our university has a hospital, and this last topic, what I described, we are working with a different hospital. What I can see that there are more and more sensors are now implanted inside human body, but the sensors are having a lot of issues. One of the issue is the size of the sensor, and the second important issue is that powering. So they're all more interested that how do you actually power the sensor. So this is a big challenge, reducing the size and powering the sensor. So in the area of the implanted sensor, these are the most important challenge the doctors are facing. So of course, in the wearable domain, the issue is that how do you actually make the wearable sensors not so power hungry? I mean, in terms of the battery, as you know that we have to charge the battery every day. Can you actually think of some extracting energy either from the body or from other different way, so that it can work for a few days to a weeks? So those are the challenging things. I mean, sensor design may not be the big issue, but powering the sensor is the biggest challenge.
So we have no more questions. So let's thank the speaker again. Thank you, Professor Subhas.
Thank you, everyone, and I hope the autumn school goes well and enjoy the time. I'm sorry I will not be able to part of it. So, and Carlos has promised me that he will show me the recording of the dance on the floor. Thank you.
Okay, that's sure. Thank you, Professor Subhas. Bye.
Okay, thank you, everyone.